Hi everyone. Today I discuss with you last section in multivariable calculus and geometry. In previous class we already discussed about principal curvatures and obliques. First corollary 8.25. The principal curvature at a point of a surface are the maximum and minimum values of the normal curvature of all curves on the surface that pass through the point. Moreover, the principal vectors are the tangent vectors of the curves giving this maximum and minimum values. Here the statement is that principal curvature at a point of a surface at the maximum and a minimum value of the normal curvature on the surface thus that pass through the point. Then the principal vector are tangent vectors of the curves giving this maximum and a minimum values. Proof: if the principal curvature k1 and k2 are different, if k1 and k2 are equal, then it is unplake. So here we consider k1 and k2 are different, and suppose k1 greater than k2, and let km be the normal curvature of the curve gamma on the surface. Then km equal to cos square theta plus uh, km equal to k1 cos square theta plus k2 sin square theta. First we substitute cos square theta for 1 minus sin square theta. Then the statement becomes k1 into 1 minus sin square theta plus k2 sin square theta. Then now take outside sin square theta, then k1 minus k1 k2 sin square theta. So km less than or equal to k1, since this k1 minus k2 sin square theta is greater than or equal to 0. Km equal to k1 if theta equal to 0 or theta equal to pi, that is the tangent vectors of gamma is parallel to the principal vector t. Now kn equal to k1 cos square theta plus k2 sin square theta. Here we substitute sin square theta for 1 minus cos square theta. Then kn equal to k1 cos square theta plus k2 1 minus cos square theta. Then now we take outside cos square theta, then k1 minus k2 cos square theta plus k2. Hence k1 kn greater than or equal to k2, because since this 1 minus k2 cos square theta is greater than or equal to 0. Also kn equal to k2 if theta equal to pi by 2. If the tangent vector gamma dot is parallel to the principal vector t2, that is k2 less than or equal to kn less than or equal to k1. If k1 equal to k2, then the normal curvature of every curve is equal to k, and every tangent vectors to the surface is the principal vector. Is a remark: let sigma of uv be a surface patch on S, then its first and second fundamental forms are e du square plus 2f du dv plus g dv square, and L du square plus 2 du dv plus n dv square. Also, the matrix of Wronskian map W is F1 inverse F11. We already discussed about F1. Is that F1 equal to matrix uh, E F F G, and F11 equal to L M M G are the two matrices. So the Wronskian map W is F1 inverse F11. Hence the principal curvature are the roots of the equation. Determinant F1 inverse F11 minus Ki equal to 0. So by solving this we get the principal curvature. And tangent vector T equal to theta sigma n plus eta sigma v is the principal vector if f1 inverse f11 minus ki into theta eta equal to 0. So we solve this equation. Also note that f1 inverse k f1 inverse f11 minus ki equal to f1 inverse into f11 minus kf1. So this is the a remark. Next is a preposition. Preposition 8.26. Let sigma uv be a surface patch of surface, and let e du square plus 2f du dv plus g dv square and L du square plus 2m du dv plus n dv square be the first and second fundamental forms. Then the principal curvature are the roots of the equation. Determinant L minus ke m minus kf m minus kf n minus kg equal to 0. The principal vectors corresponding to the curvature k are the tangent vector t equal to theta sigma u plus eta sigma v, such that L minus ke m minus kf m minus kf n minus kg into matrix theta eta equal to 0 vector. Here the proposition says that we have a surface patch sigma uv and gives first and second fundamental forms. Then the principal curvature are the roots of the equation. This determinant 1 minus ke m minus kf m minus kf n minus kg equal to 0. So this equation to solve the principal curvature. And next principal vector t theta sigma u plus eta sigma v to solve corresponding vector form L minus ke m minus kf m minus kf n minus kg into determinant theta eta to 0 vector. Now proof. We have metric Wronskian map w with respect to basis sigma u sigma v of the tangent plane is f1 inverse f11, where f1 equal to e f f g f11 l m m n. Hence, the principal curvature are the roots of k of the equation determinant f1 inverse f11 minus ke equal to 0. Then the since values of w are determinant w minus ke equal to 0. So to find the value of values, also tangent vector t equal to theta sigma u plus eta sigma v is a principal vector if if f1 inverse f11 minus ki into matrix theta eta equal to 0 vector 0 0 0 matrix 0. This put as equation 1. Here eigenvectors is given by uh, xi minus uh, ki into matrix theta eta equal to 0 vector 0 matrix. Now f1 inverse f11 minus ki equal to now substitute for k as I is I equal to f1 inverse into f1. So this statement becomes f1 inverse f11 minus k f1 inverse f1. Now take outside f1 inverse. So this can be written as f1 inverse into f11 minus k f1. Then find modulus. So modulus of f1 inverse f11 minus ki equal to modulus f1 inverse into modulus f1 1 minus k f1. Since f modulus f1 inverse not equal to 0, then f1 minus k f1 equal to 0. So that is we get modulus f11 minus kf1 equal to 0. That is the determinant l minus ke m minus kf m minus kf n minus kg equal to 0. So the equation 1 has non-trivial solution if and only if determinant f11 plus f11 plus so determinant f11 minus k f1 equal to 0. Then we solve that is theta and eta satisfy this matrix equation. L minus ke m minus kf m minus kf n minus kg theta eta equal to 0 matrix. Next is an example 8.27. Note that a sphere curves same amount in every direction and at every point of the sphere. So a sphere curves same amount in every direction and at every point of the sphere. Then the principal curvature of a sphere are equal to each other at every point and are constant ever the sphere verification. So sphere curves are same amount in every direction at every point of the sphere, then the principal curvature of a sphere are equal to each other at every point, and that constant over the sphere verification. Now consider unit sphere a square. Then we have E equal to 1, F equal to 0, G equal to cos square theta, and L1 L equal to 1, M equal to 0, N equal to cos square theta. So we have given that the values of E, F, G, L, M, N. Then we can find the principal curvature are the roots of determinant L minus KE, M minus KF, M minus KF, N minus KG equal to 0. Substitute the values L, M, N and uh, E, F, G in the equation. Then it becomes 1 minus K, determinant 1 minus K 0, 0 cos square theta minus K square K cos square theta equal to 0, and solve the equation. Then 1 minus K into cos square theta minus K cos square theta equal to 0. If the value of K equal to 1, therefore every tangent vector is a principal vector. Next example, 8.28. Now we consider a unit cylinder with a parameterization sigma uv equal to cos v sin v u. Here the values of E, F, G, E, L, M is E equal to 1, F equal to 0, G equal to 1, L equal to 0, M equal to 0. Then the principal curvatures are the roots of we know that determinant L minus Ke, M minus Kf, M minus Kf, N minus Kg equal to 0. So substitute the values, then we get 0 minus K, 0, 0, 1 minus K equal to 0. So solve this equation. Minus K into 1 minus K equal to 0. So K equal to 0 or K equal to 1. Any principal vector corresponding K equal to K1 equal to 1 satisfies the equation. Matrix minus 1, 0, 0, 0, theta 1, theta 2 equal to 0, 0. Now we solve this equation. Theta 1 equal to 0, so that T1 equal to 0 sigma u plus sigma v, and that is T1 is a multiple of sigma v equal to minus sin v cos v 0. Similarly, any principal vector corresponding K2 equal to 0 satisfy the matrix equation, 0, 0, 0, 1 into theta 2 eta 2 equal to 0, 0. So eta 2 equal to 0, then t2 equal to theta 2 sigma u plus 0 sigma v, that is theta 2 sigma u. So t2 is the multiple of sigma u, which is equal to 0, 0, 1. So here today I discuss with you a corollary and a preposition and example on the topic principal curvatures. Thank you.